Okay. All right. Well, as those of you who turned in homework 1 know, I graded them. And, well, everybody lost points on something. So, and in some cases, the same thing. Like, I mean, if a problem is to implement write a MATLAB function, then there were specified inputs and outputs, so you have to stick to that. Like Gauss Elimination returns a single matrix LU to save storage, where the lower triangular part contains the multipliers and the upper triangular part contains U. That was one particularly common mistake. But well, it's on the email what mistakes you, what points you lost. So as far as homework 2 is concerned, because homework 1 was optional, so I was waiting to see if more people were going to turn it in, but I ended up just getting 7, which I guess is not bad. So now homework 2, which is required, only 7 of 11 people have turned that in. So I'm still waiting for everybody else, and then I'll get through those too. And as far as upcoming assignments, so I just put one out on Chapter 5. I just want to make sure that I get some problems in for Chapter 5 as well as Chapter 6. Okay, and I don't finish covering Chapter 6 until like the middle of a month. So yeah, my deadline for my due date for Chapter 5 homework may have been a little too aggressive. Okay. Because I think there'll still be time to have something on Chapter 6. Because I'm covering some other stuff in the last 3 classes of a semester, trying to get a little something related to like numerical linear algebra perspective on machine learning. I don't know what I'll be able to do as far as problems for that. So, I mean, I just don't want a situation where, I mean, yes, I'd like to be lax on deadlines, but I also don't want a situation where there's a ton of stuff dumped on me at the end of a semester. And yes, I actually have had that happen. Well, mostly in undergrad classes, but I mean, whatever's in my pile at the end of a semester, I will grade it. I might grade it angrily, but
you don't want that.
Yeah, but I will. So okay. So I still need to go through Chapter 6, which I will start today, and figure out like what problems to give and all that. So what I'd like to give at the end of a semester, because we're covering eigenvalues, is what I've done in the past in this class is for Chapter 6 eigenvalue material, I give you all a choice. So you can do an assignment that's kind of like the other ones, where there's a mix of problems involved where you're proving a little something, or you're implementing rather small programming tasks, like you write a function to do this. So that's option number 1. Option number 2 is having one larger programming problem. So if you just hate proofs of any kind, then you can do this one. And if you prefer coding, where you're actually implementing the algorithm I'm going to cover soon about finding the eigenvalues of a symmetric matrix. So the QR algorithm that I'll cover. So you'll see. Details will be forthcoming about one option versus the other. But whatever it is, it's something that we do like at the very end of a semester, like during finals week. So okay, so something for you to look forward to. Okay. What?
I just said no.
Okay. Okay. Well, I imagine I guess you would choose the other option. But
Option C. Give up, quit, drop out.
Well, option C might really be a C.
Okay.
Okay. dealt with eigenvalues from time to time for various problems, but have never talked about how they're actually computed. And actually the same is true of singular values. We've seen the singular value decomposition for these squares, but I've never said anything about how you compute that either. So all of that's going to be unmasked in this chapter. So today I'm just going to start in the first section, 6.1, and actually today and Monday. So a rather large introductory section about the basics of eigenvalues, and then after that I'll start getting to methods for actually computing them. Okay. So the thing about eigenvalues is they're one of the most important concepts in linear algebra, but it's easy for a USM math major to, well, it's too easy for a USM math major to avoid them. Not intentionally. Our curriculum allows this avoidance because eigenvalues are supposed to be covered toward the end of the first linear algebra course, 326. But it seems like most of the time, whoever's teaching it doesn't get that far. And they do appear in the second linear algebra course, 426, which we haven't offered in about 5 years. And if you have taken a PDE course, they do show up there, but not everyone takes a PDE course. So I guess it's left to me. Like a great many other things. So what are, hopefully by now you know what an eigenvalue is, but I know your memories, I leave nothing a chance. So start with the most basic. So non-zero vector x, and we'll just assume, well, actually, I need to allow it to be complex. So non-zero vector x, and I want to emphasize, it absolutely must be non-zero. In fact, I once reviewed a linear algebra book that said, like, in 5 different places, it must be non-zero. One of the reviewers literally called it silly. Is an eigenvector of an n by n matrix A. So we're only dealing with square matrices now. If we have this relationship, AX equals lambda times x, where lambda is just a number, a real or complex number. And so lambda is called an eigenvalue. And we say that it's an eigenvalue corresponding to x, or x is the eigenvector corresponding to lambda. So eigenvalues and eigenvectors go together in pairs, if you will. And in fact, we sometimes call that an eigenpair. Eigenvalues have not always been called eigenvalues. They used, like, if you look at older books, they were called like proper values or characteristic values. But at some point, someone German got a vote and said that it should be eigenvalue. It's like, okay, whatever. Okay. Now, let's see. Now, the reason why, and this is something that'll become clear later, but one thing I can point out just from what I've written on the board as to why eigenvalues and eigenvectors are important. If you look at the two operations being performed in this equation that happen to give the same result. So what we have here, matrix vector multiplication, or as I often abbreviate it, a MATVEC. So that's order n squared floating point operations. And so we see the formula for it. It's a rather tedious operation. So computing each entry of a result involves a summation. Whereas on the right side, we have a much simpler operation, scalar multiplication. So all you're doing is scaling a vector x by this constant or scalar lambda. And that requires only order n. Well, actually, not just order n, exactly n. Well, if everything is real, it's n multiplications. If it's complex, then it'd be a little bit more. So, in other words, this normally complicated operation happens to be reduced to a much simpler one in the case of multiplying by an eigenvector. And this has huge ramifications for solving problems that involve, where the solution involves a matrix function. A function of a matrix could be, for example, the inverse. So f of x is 1 over x. So 1 over a, I can't really say 1 over a, but it's the inverse. Or the exponential. So the exponential of a times a parameter can be drastically simplified using eigenvalues and eigenvectors. So anytime you take a function of a matrix, computing matrix functions is made so much easier if you're able to get the eigenvalues and eigenvectors. So for example, solving ax equals b is suddenly drastically simplified. Solving a system of ODEs is now drastically simplified because that involves a matrix exponential. And therefore, PDEs that lead to systems of ODEs. So now eigenvalues and eigenvectors, unfortunately, in most cases are not easy to get. But if you can get them efficiently, then it's really a game changer as far as solving these kinds of problems because you have a much simpler way to express the solution. And that's really a central ingredient in my research program, is to try to find eigenvalues and eigenvectors in cases where previously we've not been able to. And so with the help of some amazing students, I've had some nice success in that lately. Okay, now, so additional terminology I need to introduce. Okay. Now, a non-zero vector y is a left eigenvector of A if it satisfies a similar relationship lambda times the eigenvector with the h. H means Hermitian transpose. So transpose and complex conjugate is equal to yh times a. So now we're multiplying by the vector on the left instead of a right. So, x, the eigenvector from before, is also known as a right eigenvector, just in case there's a need to distinguish. Now, mostly we deal only with right eigenvectors. So the left eigenvector rarely comes up, but it's something I wanted to make you aware of. Okay, and what you can show is if I take the Hermitian transpose of both sides of this equation, then this would give me AHY, and that is equal to lambda complex conjugate times y. So in other words, if y is a left eigenvector with eigenvalue lambda, then y is also a right eigenvector of a Hermitian transpose, and the eigenvalue is conjugated. So because there's a simple relationship between, because a left eigenvector one matrix is a right eigenvector of another. That's another reason why we don't deal with left eigenvectors often. But they're not entirely useless. We do need them from time to time. Okay. Now, to get a start on trying to actually obtain eigenvalues, if I take this relationship that is satisfied, that defines them, ax equals lambda x, and I just move everything to one side. So ax minus lambda x is 0. And now factor out an x to the right. So then I have a minus lambda times identity x is 0. Now, what we have here is this matrix times a non-zero vector is the 0 vector. So what does that tell us about the matrix? So if you can multiply a matrix by a non-zero vector and get 0, what kind of matrix is that? What? All right, so if you have a matrix times a non-zero vector gives you 0. Well, that would work, but it doesn't have to be the 0 matrix. Well, even if a matrix itself is not 0, what property of a matrix is 0? What?
Would the eigenvalue have to be 0? Or have to equal A?
Well, wait, say again? I think he had something.
It would be A minus A, so then make it the whole thing 0.
Oh, go back to what he said earlier.
The eigenvalue have to be 0?
Well, yes, 0 is an eigenvalue.
The eigenvalue have to equal something times the identity and make it equal A.
Well, okay, the first thing you said was right, that this matrix does have a 0 eigenvalue. So if a matrix has a 0 eigenvalue, what else do we know about a matrix like that? Or even just going back to this property, matrix times non-zero vector gives you 0. Okay. What? No. Were you going towards orthogonal or? No. More like the opposite of orthogonal. Okay. Good try, pal. Anyone else? All right. There actually was a problem from homework 1 involving this situation where you're assuming that a matrix times a non-zero vector is 0. Although not everyone did that particular problem because some had the wrong version of a book. No other attempt?
Okay. We've established that one of the eigenvalues has to be 0.
Yes.
And we have a non-zero vector.
Yes.
And it's not orthogonal.
Right. Because an orthogonal matrix would not have a 0 eigenvalue.
Or a 0 matrix.
No.
We're stretching.
Although one word in there is helpful.
Symmetric.
No.
Positive.
The S in SVD does not mean symmetric. Singular. Yes.
No, symmetric positive definite.
What?
Symmetric positive definite.
No.
No? Well, I don't know where I've
That also doesn't have a 0 eigenvalue.
Well, I
No. Singular.
don't know where I've been.
2 years.
Okay. All right. Because a matrix is singular if it only has a 0 eigenvalue. What else is 0 for a singular matrix? Whatever quantity that's matrix related. Determinant, yes. And, well, when I talk about determinant later, you'll see why the two are equivalent. We have a 0 eigenvalue and a 0 determinant. When a matrix is singular, what else do we call that? That's maybe a little more descriptive of, or better yet, a singular matrix is not invertible. Well, that is a rather cumbersome description. Does that mean we can say it's vertible? We should put that out there. See if it sticks. A vertible matrix. Okay.
I'm not speaking anymore.
Okay. All right. I wish I hadn't done that because that's going to stick in my head. But okay. All right. So as mentioned earlier, that the determinant of a singular matrix is 0, and that's the property that is most useful to us here. So determinant of A minus lambda identity is 0. Okay. Now, if you were to work out this determinant, which key point has an unknown in it, lambda, so that's because your variable. So this is a polynomial of degree n, where n is the size of a matrix, n by n. And that has a name, and it's called the characteristic polynomial. Okay. So what we can say is the eigenvalues of A are equal to the roots of the characteristic polynomial of A. Okay. Now, so when eigenvalues are taught in a first linear algebra course, I know it doesn't happen every time here, but it's supposed to. Chances are, the only problems that would be given to the students for computing eigenvalues is give a nice small matrix, 2 by 2, maybe 3 by 3 at the most, where you can actually form the characteristic polynomial in a reasonable amount of time. So you get some quadratic or cubic equation, and then find the roots of it, and those are your eigenvalues. And then what you can do is substitute the eigenvalues back into here, and then solve this system of equations for each eigenvector that goes with those eigenvalues. So that's how it's done, on paper for a very small matrix. But what we're going to see for computing eigenvalues is nothing to do with that. That's the thing about those kind of linear algebra courses. Yes, you learn some fundamental concepts, but as far as the actual problem solving, totally unrealistic. So that's one of the points of this class for linear algebra is to get real, even though our solutions can be complex. Yes, that was terrible, I know. But and in fact, because they're roots of a polynomial, that explains why even if a matrix A is real, and therefore the characteristic polynomial would have real coefficients, the eigenvalues can still be complex. But they would occur in complex conjugate pairs, at least. All right. Now, some more terminology. But another consequence of being polynomial roots is you can have n eigenvalues for an n by n matrix. Now, those eigenvalues might repeat, just as polynomial roots can. So all eigenvalues, accounting for multiplicities, you can only have n of them. So in other words, there are at most n distinct eigenvalues. Okay. All right, so that's one of the reasons why one of the old names of eigenvalues are characteristic values. So I guess no one wanted to call this an eigenpolynomial, thankfully. Okay, so more terminology. So the spectrum of A, and it's given by a shorthand, just lambda of A, is a set of all complex numbers that are eigenvalues of A. So the set of all eigenvalues, which can include at most n distinct elements, that's called the spectrum. All right. And the reason why I mentioned that term, which I'm actually not going to use very often, is it leads to this term. The spectral radius of A, which is denoted by the Greek letter rho of A, so it's not P of A, and that is the absolute value of the largest eigenvalue. So think this way: if you took all the eigenvalues of A and you plotted them in the complex plane, so you have your real parts on the x-axis, imaginary parts on the y-axis, and then you drew the smallest circle that you could around those eigenvalues in the complex plane, the center at the origin, the radius of that circle would be the spectral radius. So it indicates the largest magnitude in the complex plane of any eigenvalue. Okay. This term we've seen before. The trace of A. That came up in a homework problem involving a Frobenius norm in chapter 4. Now that is defined to be the sum of all of the diagonal entries, but it is also the sum of all of the eigenvalues. So here I'm numbering the eigenvalues, like lambda 1, lambda 2, up to lambda n. So the sum of the diagonal entries equals the sum of the eigenvalues. Yes?
Is that II
Oh,
or IJ?
this is II. So diagonal entries only. And then, so if you're going to give a determinant of A, that is the product of all of the eigenvalues of A. All right, so a trace is a sum, the determinant is a product. So that explains why, if you have a singular matrix, it has a zero eigenvalue among its eigenvalues, and also a zero determinant. Those two go hand in hand. Okay. Now, so if I look at a 2x2 matrix, generic one, entries A, B, C, D, then if I look at determinants of A minus lambda identity, now I use the absolute values symbols to convey determinant because it's a common notation. So then I can work out the determinant. It's A minus lambda, B minus lambda, minus BC. So then if I were to FOIL that out, so I would get lambda squared minus a plus d lambda plus ad minus bc. But then I can express that as lambda squared minus the trace of a lambda plus this expression, which is the determinant of a. And if you've dealt with enough quadratic equations, like in the zone, then you would hopefully know that the this coefficient here minus that coefficient, that's the sum of the roots, and this number here is a product of the roots if its coefficient is 1. So that's what we see in this case. So you could use a quadratic formula then to write down the roots. So the roots would be lambda equals 1/2 the trace of a plus or minus 1/2 square root of trace squared minus 4 times the determinant. So from there, you can see if you add the eigenvalues, this would cancel out, you get the trace. And if you were to multiply the two eigenvalues from a plus and then a minus, after simplifying, you wind up with a determinant. Okay. So questions about that? Bless you.
Excuse me.
Okay. Now, in MATLAB, you have we'll talk about these two functions that are closely related, but perhaps not in the way that you think. So if you call function EIG of A, and if you just that usage, so that gives you a vector of all the eigenvalues of A. And if you do this function, roots of P, that gives you the roots of a polynomial described by P. Now what is P? In this case, P is a row vector containing the coefficients of a polynomial from highest degree to lowest. So as an example, roots of this vector, if I do 1, -3, 2, gives you, that's the roots of a polynomial, x squared minus 3x plus 2. So that gives you the output 1 and 2, the roots. Okay. All right. Now, I mentioned that the eigenvalues of A are the roots of A's characteristic polynomial. Now, based on, if you had seen eigenvalues in a ordinary linear algebra class, how many of you actually have? Oh, okay. All right. Okay. Or in 326 or anything? Or?
It was in my 326 at the tail end for like 1 class.
Oh, well, it's better than nothing. Okay. All right. So you might think that this function, eig, would form the characteristic polynomial of the matrix you give it, and then call roots to get the roots of that characteristic polynomial and therefore the eigenvalues. But not only is that not what happens, what actually does happen is literally the opposite of that. So I does not depend on roots. In MATLAB, roots depends on Eig. So what roots actually does is what it does is it forms the companion matrix of the polynomial p that you give it. So let's suppose that your polynomial p of lambda has these coefficients, a0, a1, a2, etc., all the way up to degree n, where the leading coefficient is 1. Okay, so it's normalized that way. So the companion matrix, which I'll call C, is this matrix. So it has all the coefficients, well, except for the leading coefficient, it has all the coefficients along the top row minus and then it has below that ones all the way down on the subdiagonal. So then there's still a 0. I'll line this up. Okay, so it's ones all the way down to here, and you have n minus 1 of them. So, and everything else is 0. And the reason for this setup is, if you were to compute the characteristic polynomial of this matrix, in other words, determinant of this minus lambda I, so the determinant of C minus lambda identity is this polynomial. So MATLAB contrives a matrix whose characteristic polynomial is the given polynomial. Okay. So once that's done, what roots computes is I of C. So it converts a root finding problem to an eigenvalue problem, whereas in a first linear algebra course, you convert an eigenvalue problem to a root finding problem. Now, how does it do that? How does Eig work? Well, that's the subject of the rest of this chapter. So that's something that's going to unfold over several class periods. Right. Yeah, so in those earlier courses, you only learn how to compute eigenvalues for cases where you can actually compute polynomial roots, which is hardly ever. I mean, quadratic, sure, certain cubics, maybe certain very special cases of higher degree, but otherwise, what are you going to do? Now, unfortunately, this doesn't always work well. And you can demonstrate that because there's another function I want to mention that's kind of an inverse of roots. So poly of a certain set of values, I'll call them R1, R2, Rn. So the values that you're given, that are given, are roots of a polynomial, and poly computes the coefficients. So coefficients of a polynomial lambda minus R1, lambda minus R2, lambda minus Rn. So roots and poly are kind of inverses of each other. So roots, you give it the coefficients, it factors it for you, gives the roots from those factors. Poly, you're giving the roots of those factors, and it will work out the coefficients. So it performs, well, foiling or just multiplying out. So what that means is these functions should undo each other. If I have some roots and I pass it to Poly to get the coefficients, and I feed the output of that into roots, should give me the same roots back. So the roots of Poly of some vector R should equal R. And if you try it out like on a simple example, in fact, too bad it's kind of a pain to deal with projector, but I'm going to try a very simple example right here and just tell you what happens. So if I do roots of Poly, I'll just give it the vector 1, 2. And it gives me back 2, 1. Well, the order may be different. But the point is the set of roots in there should be the same. So for a simple case like that, yeah, it was fine. But what if you try a larger example? In fact, there's one example. If you give it the numbers 1 to 20, the integers. Then the output that it gives you, and so you can try this yourself in MATLAB. Roots, Poly, 1 to 20. And this is called Wilkinson's example, to show how polynomial root finding by way of creating eigenvalues are really just a problem no matter how you try to solve it. It can sometimes be a badly conditioned problem. So the output that it'll give you is not the numbers 1 to 20. You can recognize them as being fairly close, but they're significantly off. For example, you get, I'll just write the first few. So you get 20.000 something, but then you get like 18.93. That's close to 19. 18.02. The next one should be 17, but you get 16.03. 16.92, and then 16.14. So it's significantly off. So that's unfortunate. And in fact, if you try roots of Poly 1 to 50, actually I'm not going to tell you. Just go ahead and try it. And you know what you're supposed to get. The numbers 1 to 50 back, and you'll see that disaster strikes. And then even worse than this. That's bad enough. Okay. Now, okay, great. Now my notes are a mess. Okay, did that. Okay. Oh, okay. I'm still doing all right on time. You still have a lot of suffering left. Okay. So, and the thing is, any other method for finding roots, like I mentioned, there's only a few cases that can be handled by hand. So for larger matrix, forget it. Can anyone think, based on like other classes and so forth, other methods for finding roots? Well, numerical methods. And many of you, not all of you, but many of you took a class from me where this came up.
When was this? 12 years ago?
One.
That's even worse. Secant Method.
Yeah, Secant Method. What's another one?
Bisection.
Yeah. So I covered 2 more.
Where are you coming from?
Well, at least somebody remembered something.
6 point.
Okay. And the best one of all.
so mean.
Because you're the only one spitting out stuff.
No?
Hold on. Give him
A second.
Well, it's numerical 2. Well, I tried to cover numerical 1, but I didn't with you guys. But numerical 2, where about half of you were in that class. What?
Associated with the mathematician's name.
Yes?
Can you give me the first word?
What?
Can you give me the first word?
First letter.
First letter.
No.
Yeah.
Yeah,
Yeah, it's Jacobi.
What?
Jacobi?
Seconds or Newton?
Newton's
yeah,
method.
Newton.
Yes. Yeah, so bisection was the worst, and then fixed point was pretty decent, then Newton's was the fastest, and then secant was slightly slower, but one could argue more efficient because it doesn't need derivatives. So yeah, you could try that. Like, you take your polynomial, if you have a decent initial guess, but that might not be practical, you can use Newton's method to find a root pretty quickly. Then synthetic division, to divide by that, to get a polynomial degree 1 less, to find another root. But then there's so much round-off error committed during that process that it's going to be even worse than this. So that's not practical either. So just like with Ax equals b, how we're going to proceed is as follows. I like the phrasing here. For which matrices can we easily find the eigenvalues? Like if it has a certain structure where it's given away. Yes. Just like for Ax equals b, which systems of equations are easy to solve? Diagonal or triangular. And then once we know that, which, yeah, I'll prove that, how to reduce the general case to one of these easy cases. So for Ax equals b, yeah, a triangular or diagonal system can easily be solved. And how to reduce the general case to those easy cases, we use Gauss elimination. So it's a similar idea here. We need to, because in Gauss elimination, you're transforming your given system equation into an equivalent but simpler system of equations. So here, same thing. We want to transform a general eigenvalue problem into a simpler eigenvalue problem. The one big difference between this eigenvalue problem versus Ax equals b is that in Ax equals b, you know you can get it done in a finite number of steps. You can figure out exactly how many steps it takes. Whereas with eigenvalues, that's not possible. You'd be carrying out an infinite number of steps. So you have an iterative method, you just have to try to get close enough as far as round-off error is concerned. So just like we've been dealing with iterative methods for Ax equals b, it's the same situation here. So that's what makes this problem a lot more challenging than the other ones we've seen. Because even the iterative methods we talk about, conjugate gradient, geometry, those theoretically will terminate after n steps. This won't. So this one really can go on forever. And sometimes it fails. Okay. So how are we going to do this? So we get an understanding of a problem here. So, okay. So first I need another term here. So we'll have a vector space W. So it's a subset of Cn, so a subset of n-dimensional complex numbers, or complex vectors. Let's suppose it's a subspace. And all I mean by that is, basically it's, for determine, well, modern algebra, sorry, it's closed. You add vectors in W, the result is in W. If you scale a vector in W, the result is in W. So not any subset has those characteristics. So it has to contain a zero vector, for example. But so the theory of W is an invariant subspace of a given matrix A if we have the following. If you have a vector x in the subspace, then A times x is also in a subspace. So multiplying by A keeps you in the subspace. That's what it means to be invariant. Now, next I'm going to make an assumption that the dimension of W is some number k, which has to be less than or equal to n. Because any subspace has an n-dimensional space must have dimension at most n. Then I'm going to define a matrix X to have columns x1, x2, xk. So this is a n by k matrix where these vectors form a basis. Whoops, got my words jumbled here. Those vectors form a basis for W. Okay. So they're linearly independent and they span all of W. Okay. So what that means is there exists a matrix B that's a k by k matrix such that A times x is equal to x times B. Now, how do I know that? Because x, columns of x are vectors in W. If I multiply any of these by A, they'll stay in W. So all the columns of this matrix belong to W. Therefore, all the columns of this matrix also have to belong to W. Well, what is this? This has the form x times b1, x times b2, x times bk. Well, those are the columns of B. What are these? These are, each one of these is a linear combination of the columns of x, which therefore is in W. So anything in W has to be expressible as linear combinations of these, but that's what these are. So that's why we can say AX equals XB. I should mention that a relationship much like this, we saw this earlier on iterative methods. You have this relationship with, like for instance, the Landshell's method, except you have an extra term here. That's the only difference. Okay. All right. So now we have a way of expressing AX in terms of a smaller matrix, B. Okay. Not only that, I have to be careful here because I have certain things that are homework problems. I haven't decided which ones I'll assign yet. It's like, do I do them or not? Well, no, but I will do this one. Okay. Now, let's suppose I have a number lambda that is an eigenvalue of B. So what that means is I have By is equal to lambda y. some vector y, k-dimensional space. Okay. So then what I'm going to do is I'm going to multiply both sides by x on the left. And because lambda is just a constant, I can move it out to the front. But xb equals ax. So now I have ax y equals lambda x y. But x times y is a vector. I'm going to group that here. So now I have a. Oh, I have to assume that y is non-zero. That's important. So now I have a times a vector equals lambda times the same vector. So what does that tell me?
Lambda is the eigenvalue.
Yes. So lambda belongs to the spectrum of A. So I assumed it's in the spectrum of B. It's also in the spectrum of A. So what that tells me in general is the spectrum of B is contained in the spectrum of A. Now B is going to have at most k eigenvalues. A has n. So if k is less than n, it's a proper subset, but the point is it's still a subset. So when we have this kind of invariant subspace relationship, we see we have containment of the eigenvalues. Right. And what's important here is, since y is non-zero, and these guys form a basis, that means they're linearly independent. That is enough to tell me xy is also non-zero. So that way it qualifies as an eigenvector. So questions about what happened there? So it's a helpful skill to be able to identify, whenever they come up, eigenvalue, eigenvector relationships. So the key is, anytime you have matrix times a vector equals scalar times the same vector, then you have an eigenvalue, eigenvector pair that you found. I've seen so many problems where it could be from a whole other area of math where this pops up, it's like, oh, it's an eigenvalue. And then chances are it's helpful to you in whatever problem you're solving. So now, I can take this to the extreme. Suppose that k, the dimension of my invariant subspace, is equal to n. So what that means is, X is an n by n matrix now. And because it has linearly independent columns, it's invertible. Maybe we should say not vertible. So now, this relationship that I had before, AX equals XB, I can multiply by X inverse. Now I have X inverse AX is equal to B, and I can also say that the spectrum of B equals the spectrum of A. So when that happens, we call that similarity. So A and B are similar matrices. And this expression, X inverse AX, so anytime you take a matrix, you multiply on the left by some matrix and multiply on the right by that matrix's inverse, is a similarity transformation. Of A. And the most important thing about that is that a similarity transformation preserves the eigenvalues. That is huge. That's the underpinning of any method for computing eigenvalues. So really what I've done is I've answered the second question I posed earlier, because I posed two questions. One, what are the easy cases for finding eigenvalues? Okay, Joe answered that, but yeah. But I'll talk about that more later. And then the second question was, how do you reduce the general case to one of these easy cases? Now, I haven't given a full answer yet, but I've just given the first step on it. We now know how to transform an eigenvalue problem into an equivalent eigenvalue problem. So if you keep the eigenvalues the same, and that is a similarity transformation. So eigenvalue finding methods work by repeatedly applying similarity transformations to A until it's reduced to some form where you can read off the eigenvalues. Now, one unfortunate thing about similarity transformation is it involves the inverse, and inverses are not easy to get. Although, what's one case that we've seen where the inverse is easy to get? What kind of matrix has an inverse that's readily available? Well, yeah, but that's not very useful here. More broadly than that. What? No. It doesn't have an inverse.
Well,
It's vertible.
it's vertible, right?
When have we seen a situation where I define something, a kind of matrix where I say something equals to identity, like that matrix times something equals identity? Yes. So if X is orthogonal, then X transpose X is identity, which means that X inverse is the same as X transpose. So the inverse is readily available in that case. So in fact, the algorithms we'll be looking at will use orthogonal similarity transformations for that very reason. In fact, orthogonal matrices that we've already seen for least squares, Householder and Givens, because we know that they can zero entries out. There's something else about that. Dang it. It flew out of my head. Never mind. Okay. So, yeah. Another good reason for using orthogonal matrices is they are perfectly conditioned. The condition number of an orthogonal matrix is 1, which is the smallest it can be. Okay. Now, dang it. I was thinking, no problem getting through all these pages in time, but I might not. Okay, well, that's okay. So I just get my pages back in order again. Okay. Now, but I want to be able to make a general statement about for which matrices are eigenvalues defined. So we now know that we can transform the eigenvalue problem to an equivalent one by doing some sort of similarity transformation, but we don't know what kind of similarity transformation. We need a goal. We need to know what kind of matrix we can get. And yes, we mentioned that diagonal would be great, except diagonal is not always going to be possible. So we have to shoot for something a little less. Now, I'm going to look at a matrix that has this structure. Let B, and this is actually the kind of situation that, from a teaching standpoint, I don't like. It's kind of like I'm pulling this out of thin air, but you can always get around it, I guess. So suppose I have a matrix like this that has this block structure. So this matrix is P by P, and this matrix, B22, is Q by Q. So P plus Q is equal to N. So therefore, this block is P by Q. But the thing is, this matrix is block upper triangular, because if we were to abstract these blocks down to single entries, we'd have an upper triangular matrix. Okay. Now, so I'm going to look at a couple situations here. Suppose I have a vector x that has this block structure, where this is the first P elements, these are the last Q elements. So what that means is, if I compute B times x, so I have B11, B12, 0, B22. Okay. So what I would get here is B11 x1 plus B12 x2. So I'm going across the row and down this column. And then for the second part, I have 0 plus B22 x2. Now, I want to look at two cases. First is when x2 is the 0 vector. Then if I just set x2 equal to 0 throughout here, then I have b x1 0 is equal to, and what I get up here, if I set x2 0, these terms are gone, and I get b11 x1 0. And then, so now, if I have this situation, if x1 is an eigenvector of this block, B11, then Bx is equal to lambda x1 0, but I can factor the lambda out. So I get lambda times x. In other words, the spectrum of B11 is contained in the spectrum of B. So any eigenvalue of B11 is also an eigenvalue of B. Okay. Because once I have this eigenvector of B11, I automatically have a way to get an eigenvector of B for the same eigenvalue, just by padding with zeros. Now, that's one case. Another case is x1 is 0. So Bx, I set x1 to 0, and what I get is B12 x2, B22 x2. Although, let's see, this isn't working out quite like I wanted. Now I want a similar situation here where dang it. I've done this problem a zillion times, except it was all years ago. So I want a similar situation. We let b22 x2, so x2 is an eigenvalue of b22 now. Okay, so then I have except x is now 0. 0x2. Okay. And now I want a result that I have lambda times x2. Okay. Bless you. We're supposed to reach the conclusion that we get lambda, the spectrum of B22 is also contained in the spectrum of B by getting an eigenvalue of the whole matrix B. Okay. Unless actually, I think I'm not supposed to consider this case. I do want the case of x2 being 0, which I've done. But then, okay, I have to change the situation. I have to make sure it comes everything. Either x2 is 0 or it's not. Okay, hold on. I'll try to recover the situation without looking it up, because then that's going to piss me off. All right. If x2 is 0, I can't do this. But now I'm assuming it's not 0, so I can do this. But I do have an eigenvector. So all right, so now I have this. And then I have lambda x2 down here. Okay. And but the thing is, ideally I need this to be equal to, okay, so what I want is b11x1 plus b12x2 to be equal to lambda x1 for whatever lambda is. Now, everything here is known except for x1. So I have b11 minus lambda identity x1 is equal to minus b12 x2. Okay. And I think I almost assigned this as a homework problem. Good thing I didn't. But now, if let's assume that lambda is not in the spectrum of B11. It's already covered by this case. We know it's an eigenvalue of B also. So if lambda is not in this matrix, what do I know about that matrix? If lambda is not an eigenvalue. Non-singular. Therefore, it is invertible. So that means I can get x1. I can solve for it. If this happens to be 0, I can set x1 equals 0, and that works too. So the point is, because it's invertible, I can get x1 that makes this an eigenvector. So that tells me lambda is again in this. So in other words, so those eigenvalues belong to the spectrum of B. Okay. Now, in the case where lambda is an eigenvalue, so this matrix is singular. All right. Well, because it, but that's where it overlaps with the spectrum of B11. So, so don't worry about that case because I already know that that number is an eigenvalue of B. So the overarching conclusion, which I apologize for my terrible board use, but I'm assuming therefore your notes, where you're not constricted by my board, will be much better organized than this. I can say that the spectrum of B is equal to the spectrum of B11 union spectrum of B22. So that's the conclusion I'm trying to reach. So in other words, if you're able to reduce your matrix to have a block upper triangular, or actually it wouldn't matter, lower triangular would work too, block triangular structure, you've just divided your eigenvalue problem in two. I can find the eigenvalues of this smaller matrix and the eigenvalues of this smaller matrix and put them together, and then I have my eigenvalues. So it's a way to reduce the size of a problem. And yes, I'm thrilled I was able to recover that without looking it up. Because the problem is, and anyone who's taught knows this, when you're up there in front of your class, your IQ just
Plummets.
yeah. So, which is why preparation is so important.
2 plus 2, 12.
Yeah. And the trouble is I can't help improvise during class, and it gets me into trouble. So, okay. Let's see. Now, so the thing is, now we have a goal that if we can apply similar transformations to A to get something like this, to have a block upper triangular structure, then we're on our way to finding all the eigenvalues. And we can keep whittling it down to have smaller and smaller blocks until you have a trivial, like 1 by 1 or 2 by 2 block where you can easily pick off the eigenvalues. So as an example of what you can get with block triangular structure, I'm unfortunately running out of time. So the big proof I hope to do, we'll have to wait until Monday, but that's okay. Right, and I've marked off some problems I know I can't assign now. Let's suppose my matrix is this. So a 6 by 6, no, 5 by 5 matrix. Okay, so I have 1, minus 2, 3, minus 3, 4, and then I have 0, 4, minus 5, 6, minus 5, and I have 0, 0, 6, minus 7, 8, 0, 0, 0, 7, 0, 0, 0, 0, minus 8, and 9. Okay. What?
What is in the third row, the fourth column?
Oh, that's a minus 7.
Okay, I know there's 2 or something.
Oh, okay, yeah. Now, this matrix can be seen to have a block triangular structure to it. Like if I can segment it like this. So this would be like my B11, and that's my B22. So then, to get all 5 eigenvalues of A, I can focus on this piece. This is my B11, and so P equals 3, and B22, so Q is equal to 2. So then, if I look at each of those matrices, well, this one is also upper triangular. So I can carve this up. I have 1 by 1 blocks along the diagonal. So the spectrum of A, therefore, includes these diagonal entries, 1, 4, and 6. Now, to get the remaining eigenvalues, I focus on this block. But this block has what structure? No. Lower triangular, which also works the same way. So I can still look at the diagonal entries. So 7 and 9. So this I didn't have to look at all. It had no bearing on the eigenvalues. So anytime you can recognize block, lower or upper triangular structure, you can just read off the eigenvalues. Okay. So what I want to do is use this idea of reducing to block triangular form to come up with a matrix decomposition that reveals the eigenvalues. Just like I did earlier for a couple chapters ago for singular values. And unfortunately, that's not something I'm going to be able to accomplish in just 4 minutes. So that would go very badly. Okay. As far as what I want to do beyond that, oh geez. Okay. Well, that's unfortunate. It's like, I'm looking at what can I cut out and all that, but like I don't want to cut out any of this. So, okay, so sure decomposition, and then, okay, so I may have to cut something out on Monday, but I'll deal with that later. Okay, so I think you suffered enough, and so we'll continue with this on Monday.